Okay, today I'll be talking on computational fluid dynamics, which is also known as CFD. Computational fluid dynamics is a powerful and versatile branch of engineering that utilizes advanced numerical techniques to analyze and stimulate the behavior of fluids, including liquid and gases. This field combines principles from fluid mechanics, thermodynamics, and computer science to provide insight into the complex fluid flow problems. The we have the governing equations in CFD. Firstly, we have the Navier-Stokes equations, the fundamental set of equations that describe the motion of fluids, including conservation of mass, momentum, and energy. We also have the continuity equation, which ensures the conservation of mass in a fluid flow, stating the rate of change of density within a controlled volume, and it's equal to the net rate of flow of mass into the volume. Thirdly, we have the energy equation, which describes the conservation of energy in a fluid flow, accounting for the interplay between kinetic potential and moving to the numerical discretization methods. We have the finite difference method, a straightforward approach that approximates their derivatives using Taylor series expansions, resulting in a system of algebraic equations. We have the finite follow method, which divides the computational domain into discrete control volumes and applies conservation laws to each volume to derive the governing equations. We have the finite element method, which utilizes a variational formulation to obtain approximate solutions, particularly useful for complex geometries and unstructured grids. The turbulence, moving on to the turbulence modeling approaches. Firstly, we have direct numerical simulations, which is DNS. It resolves all the details of the turbulent flows, providing the most accurate but computational intense approach. Secondly, we have the Reynolds average Navier strokes, that's the RANS, which models the time averaged effects of turbulence using statistical approaches to close the governing equations. Finally, we have the large eddy simulations, that's LES, which resolve the large energy containing turbulent eddies and models the smaller, less important eddies, balancing accuracy and computational cost. Moving on to the CFD simulation workflow, geometry modeling, which is the creating of a digital representation of the physical system to be analyzed. We also have the mesh generation, which is discretiz- discretiz- discretizing the computational domain into a grid of cells or elements. We have the solver setup, which defining the boundary conditions, initial conditions, and numerical schemes to solve the governing equations. We have finally the post-processing, which analyzing the simulation results, visualizing the flow patterns, and extracting relevant data. Applications of CFD, we can see the applications of CFD at the aerospace engineering, which is the analyzing airflow around aircraft, optimizing wing designs, and predicting aerodynamic performance. We have automotive engineering, improving vehicle aerodynamics, studying engine combustion, and evaluating the HVAC system performance. We have the energy systems, which is simulating the flow of fluids in power generation, oil and gas, and renewable energy systems. We have the environmental engineering, which is modeling atmospheric and oceanic flows, predicting pollution dispersion, and studying natural phenomena. Advantages and limitations of the CFG. Improved insight. CFD provides detailed quantitative insight into fluid flow phenomena that are difficult or impossible to obtain through physical experimentation alone. Time and cost saving. CFD simulations can be conducted more quickly and cost effectively compared to physical prototyping and testing. Limitations and accuracy. The accuracy of CFD results is dependent on the quality of the numerical models, computational grid, and input data, which can introduce uncertainties. Then, high computational future trends and developments in CFD. One, we have the increased computational power in advancements in high performance computing and parallel processing will enable higher resolution simulations and exploration of more complex fluid flow problems. Integration with machine learning. The integration of machine learning and artificial intelligence techniques with CFD will enable the development of data driven models and predictive capabilities. We also have the improved turbulence modeling. Ongoing research into turbulence modeling, including the development of hybrid Ransless approaches, will enable the accuracy and reliability of CFD simulations. Finally, we have the multi-physics simulations, coupling CFD with other physics-based models such as structural analysis, heat transfer, and electrochemistry will enable more comprehensive and realistic simulations.